Okay, hello. Thank you so much for joining us today on this talk about tiny MLOps. So what we will be doing is we'll be talking about what tiny MLOps is, give an overview of the different of a tiny MLOps pipeline, and then talk about the different tools and the tools available for building tiny MLOps pipelines, and finally talk about some of the challenges that there are in building such pipelines right now. So I'm Soham. I'm currently working as an ML engineer. And with me today is also Archana, who is also working as an ML engineer. Yeah, moving ahead. So before I begin, I just want to acknowledge some of the people who have kind of helped us prepare for this talk. First of all, we want to acknowledge Professor Vijay Reddy from Harvard. We had a lot of discussions about tiny MLOps and some of the challenges and tools that are that are currently there in tiny MLOps. And more specifically, Prof. Vijay talked to us about how feature engineering and data drifts can affect any tiny MLOps pipelines and how we can account for that. We also want to thank Aurelian and Alessandro from Edge Impulse. Aurelian especially has been helping us a lot by showing us some of Edge Impulse's tiny MLOps features, and he is also like we've been talking a lot about over-the-air updates as well, and that was also really helpful. Finally, we also want to really thank Edge Impulse. They're the reason that we are here and able to kind of get this platform to talk to you about this. And also, they do a lot of really great community work and a lot of research discussions and paper reading and discussions of projects, and those really kind of help us learn more about these things and kind of grow as a community. Okay, so moving on. So yeah, like I mentioned, we'll be talking about tiny MLOps today. The first thing we'll be talking about is what MLOps is actually, because not a lot of us may know about it. And then we'll kind of shift gear and then talk about what tiny MLOps is and how it compares with MLOps. And we'll then show you like a typical tiny MLOps pipeline. And the parts of those pipelines are like training, optimizing models. Then we have to kind of benchmark and deploy those models as well. And each of these parts have different challenges, different frameworks, and different tools. And we'll talk a bit about those. And finally, we'll show like a case study of a tiny MLOps pipeline and using Edge Impulse. Okay, so with that, like let's get started. Um, so what is MLOps actually? Um, for me, right, MLOps is kind of like trying to combine all the good practices from data science, DevOps, and machine learning, and kind of combining all of them together and and taking all of those best practices to be able to deliver these machine learning models to end users who will use them, and also to do it at scale and in production. This is actually not as easy as it seems to be. There's a lot of problems that can come up when you're deploying ML models. Stuff like versioning the data, versioning machine learning models itself, and also like taking care of how you collect the data and how you feed that data into the model. And finally, how do you account for, like, let's say, making sure that the model keeps performing well on that data and it doesn't drift and give weird predictions because, let's say, the input data changes. And so yeah, so when we try to like combine all of these best practices from all of these different fields, we get like it's only then that we are able to deploy machine learning models really well and really easily. Um, but then tiny MLOps is a bit different. And this is because tiny ML is vastly different from normal ML. In normal ML, like when you deploy a model, you're not usually resource constrained. But in case of tiny ML or edge computing in general, you often have to, like, you will have to kind of deploy models to these really tiny microcontrollers, which don't have a lot of features and which don't have a lot of compute power or memory. And those and you know, because of that, when you prepare models to be deployed to these devices, you have to perform some extra steps like optimizing your models. And these are not these are steps that a typical MLOps pipeline does not really support. Also, some steps need to be kind of improved and augmented, and you need to add, you know, more tasks to those steps, so that you know they're better suited to TinyML. So, for instance, you know, when you're benchmarking your model or your device, you also need to benchmark your model's latency, throughput, as well as energy consumption, which are not really huge you know, requirements for standard MLOps systems. And this is why we need tiny MLOps. So moving ahead, I want to talk a bit about like what are the similarities between these two fields, and then you know, and then we can talk about where they actually. So in both of these cases, we have to like acquire data, and then once we acquire it, we also have to analyze it and process it. In the case of uh, like tiny MLOps, how the data is collected is it needs to be a bit different from standard MLOps. So, for instance, because a lot of data we use depends on sensors, your sensor can be like an issue when you're collecting data. So, for instance, if you're collecting data on a sensor that has a different range or a different precision from the sensor that you will use when you deploy it, when you deploy a model, that will cause issues. Also, like in, you know, you have to also do like feature engineering in both the cases, but then how you do feature engineering for MLOps is a bit different. And also like because we're deploying our models on like resource constrained devices, how much feature engineering we do can increase latency, and so we need to kind of think about that before we actually deploy a model in like deploy a TinyML model. In both cases, we also actually like train our models with like hyperparameter tuning or some form of neural architecture search. But when we actually do it for TinyML, we need to be mindful of the fact that our end device will not have a lot of computational power or memory, and so when we do hyperparameter tuning or when we do NAS, we need to keep that in mind. Right. We also need to use architectures, so like model architectures that are more suited for deploying to resource constrained devices. You know, like architectures like, let's say, efficient net or mobile net. And finally, also need to do like some risk analysis and some performance testing. But in the case of TinyML, you know, it has been shown that when you optimize models, your bias increases, or you know, like underrepresented classes are like impacted more after optimization. And so we need to kind of think about these aspects as well, like the security and the robustness aspects of our model. And we'll be covering a lot of these steps later on as well. Um, but then this is kind of where the similarity ends, and there's actually a lot of differences. And I think the biggest difference is that when you're deploying a model for like for MLOps, you're actually deploying it on like super powerful devices, which have like a lot of memory, which have support for a lot of different compilers, a lot of different instruction sets and ops. Whereas in the case of like smaller models, and TinyML models, you know, like the device you deploy to is going to be a constraint, and so you know, when you deploy them, you know, your device may not, for instance, support many operations, or it may not support like some kind of layers. And so when you're training your models and optimizing it, you have to keep these things in mind. Also, in case of MLOps, the things that are like more important are like accuracy of your model, as well as like, let's say, availability. So availability is, you know, how often does, let's say, the model go down or is not available to make a prediction. But these are really not issues for TinyML. On the other hand, like in TinyML, what we need to think about more is stuff like latency and throughput. and how much power our model is consuming. Um, and like other metrics like accuracy may not be as important as some of these metrics. Also, containers is something that you kind of have to like do when you're building MLOps pipelines. You have to use containers. You have to do continuous integration and deployment. You have to log all of your data, and you have to kind of monitor how well your model is doing. And these are all things that are easy to do. There are like a lot of tools to do them. But then in tiny MLOps, there's like no container technology. If you want to log or if you want to monitor, then that'll increase your energy consumption, will increase your latency and the memory that your device needs. And so it makes these things difficult to do. Um, Also, because of how resource constrained we are, it's also difficult to actually check when the model is deployed, how well it is performing. And if it's not performing well, it's also difficult to update it. Um, Whereas in case of like MLOps, it's kind of really easy to do that. You can check performances regularly and really easily, and you can update it. You can also, like, let's say if your model is running slowly, you can just add another CPU or a GPU and distribute your model across those devices, and you can like get extra performance. And that's what robustness and auto scaling is. But that's like not really possible to do in TinyML either, because it's really hard to scale your hardware after you deploy it. You can't like just add another microcontroller and expect your latency to go down by half. That doesn't happen. Also, because our models are deployed in the wild, out in environments where, like, I don't know, there could be like sunshine, rain, heat, dust, stuff like that. It's also important that your system is really robust. And these are not like issues that you have to take into account um, when dealing with MLOps. Okay, so now that we know what the differences and the similarities are, I want to talk about a standard tiny MLOps pipeline. Um, and this pipeline is kind of like it doesn't in it has components which are different from what a standard MLOps pipeline has. So how we collect data and how we pre-process it for training our models is going to be almost same for MLOps as it will be for tiny MLOps. So I don't like, we haven't really added that here. What will be different though is you have to actually deploy model, like where you train your model and optimize it will be different from the device that you deploy it on. And we call this first set of device, like first device, the host device. So that is where you usually train your model. And once you have trained it, you optimize it, and then you get a model file. Um, After you get your model file, you also have to benchmark your model. And some of these benchmarks you can run on your host device, but others you have to run on the actual device. So benchmarks like, let's say, the size of the model, the accuracy, these are things that you can easily measure on the host device. But then other metrics like, let's say, the latency or the energy consumption, that'll change like vastly from different devices, from different like deployment devices. So these are things that you have to measure and do on the device. So benchmarking, it kind of sits in between where you have to do it in both of these devices. But what you have to do on devices, you have to deploy it. And then after you deploy it, you have to monitor it. You have to monitor how well your model is performing or your system is performing. And if there's an issue, you have to update your model, right? And you also have to think about the security and the robustness of your model, on the device. So let's kind of talk about this, one by one. The first one thing I want to talk about is training your model. Training your model for TinyML, you might think it's the same, but like as training like a normal model, but it's not. Because when you train a model for TinyML, you need to think about, like, let's say, how much can this model be optimized? And does this model use operations that are supported on my target hardware device? You also need to use efficient architectures to train your model. And finally, you need to, think about your target hardware and like aspects like how much energy does my model consume to run, and what are the latency, what's like the latency of like target latency of my model. So these are things that you have to think about. And so when you actually go and try to train models for TinyML, I use this technique called look ahead method. And what I mean by that is when you are training your models, you need to it helps to be aware of the requirements of your target system and any constraints that the target system will have. Um, and if you are aware of this, then it gets really easy to make architectural choices and choices of the kind of operations and layers you will use in your model. um, so what do I mean by that? So we know for a fact that when we before we have to deploy a model, we need to optimize it, right? So if we can look ahead and think about optimization, then that makes the job of training our model like easier, right? So for instance, if, we know that when we optimize our models accuracy, or in case of regression, like mean square error or something, it will decrease. Um, so can I train, um, so how can I like train my model keeping in mind that this will happen? Also, because we'll be eventually deploying our model on some hardware, it also helps to like look ahead and think about the hardware as well. Specifically, like how can I create a model architecture that is going to be supported on my target device, and it fits basically on my target device, like meets all the latency and memory constraints, right? um, and and so when we try to do this, the two things that in my opinion are really important are the model architecture and the model ops. By ops I mean operations. So in case of architecture, like you have architectures that are specific for edge computing devices like mobile net and efficient net. Also, when you're using operations, it's kind of important that you use really simple operations, like kind of like the basic ones, and really simple layers as well. And it's also important that you not use data flows that are really complex. And an example I have of this that I've faced in when I've been deploying ML models is if you look at the number of operations and the size of like ResNet models, like the number of operations needed to execute it, it's actually really less as compared to like a larger model like Inception. But then ResNet has like some really weird like data flows internally, and so when you actually go to deploy it, your ResNet architectures actually, like in my experience at least, perform much worse than architectures much larger to it, like Inception. And I theorize that this is because of the kind of complex data flows that ResNet architectures have. Um, so yeah, so it's kind of really difficult to kind of tell how complex your or just based on the operations, how much time it'll take to execute your model. So when you're training a model, it helps to keep these things in mind so that you don't have to go repeat these steps later on. Okay, so how do we actually go about training our models, right? So we need to think about like the training frameworks that we're using, and we need to kind of make sure that our frameworks support optimization, first of all. And it also needs to support the architectures and operations that our final hardware supports. And it also helps if there are tools in that framework for TinyML, right? And like I know of only like two of these, which is like TensorFlow and PyTorch. Um, Also, like if like thinking about algorithms, you can train your because you know your model will be optimized later on. You can do quantization aware training, and that kind of helps reduce the accuracy drop that will happen when you quantize your model later on. And also, there's like a lot of techniques for neural architecture search that are specific for TinyML, that you can also use to kind of reduce your accuracy drop, right? Okay, moving ahead, the next step is after you train your model, you have to like optimize it. So optimization is this process that we do to reduce the size of a model, as well as the number of operations that that the model needs to execute, so that they can fit on edge devices. Um, the good thing about optimization is, I'm sorry, not the good thing. Like the bad thing about optimization is that when you do it, you usually get a reduction in accuracy. Also, there's some really nice work by researchers like Sarah Hooker, that show that optimization can actually increase biases. Also, many optimization like techniques actually may not increase the performance on your hardware device, like even if you do it. And like a really pruning is like a really bad algorithm right now. Even though we can prune models really well, and reduce like a lot of operations and a lot of weights. Prune models aren't really supported that well on most microcontrollers and most even like CPUs and GPUs, right? Um, and so even though on paper a pruned model may look like it'll perform really well, and that it's small, in reality it doesn't, because our hardware can take advantage of the pruned models. Um, Also, int8 operations may not actually be fast on many systems. So this is in case of quantization. This is especially the case for like Linux based embedded systems, so like Raspberry Pis, where you might see that even if you quantize a model to int8, the performance increase, like the decrease in latency is not going to be a lot than a floating point model. And this is because like the floating point units in these devices are actually like really well made, really powerful. So you don't really get much savings. You do get savings in memory. Int8 models will take up like 1/4 the memory of like a floating point 32 bit model, but your latency may not actually decrease much. So these are some of the challenges that we face when optimizing models. Um, so how can you like overcome them? The best again just like the look ahead method is like super powerful for this. So make sure you look ahead to the hardware that you are going to deploy to. So if you keep in mind the hardware you're deploying to while optimizing, then you can overcome some of those challenges. So for instance, if your hardware does support a model that can do pruning, like that can support pruned models, then do pruning, and you won't get as much performance degradation. Or if you're deploying to a hardware device that has a floating point unit, for instance, let's say an Arduino Nano, right? The Nano 33 BLE Sense. It does have a floating point unit, and just check if the performance of executing your model with floating point arithmetic is if it's comparable to doing it with int8, then there's no need to really optimize your model at all, right? But even if you do have to optimize, there are a few algorithms for that, and quantization is like the most widely used algorithm for that. There's also pruning, and my favorite is like knowledge distillation, where what we do is we take like a really large trained model and we distill the knowledge of that model into a smaller student model. Um, and surprisingly it actually works like really well, which like for me I find like really interesting, and I really like playing around with this. Like in my personal experience, this is the kind of algorithm that works really well. um, there's also some tools that you can use for optimizing. So for instance, TF Lite is probably the most commonly available tool. There's also Edge Impulse, right? OpenVINO is like a tool that is supported by Intel devices. And if you're deploying to like, let's say a neural compute stick, OpenVINO is the only tool that you can use for that. There's also ONNX, which is really good for interoperability. Um, and the reason I'm talking about tools is because what you use to optimize and train your model is what will, like it's the file that you will get, like the model file. And your end hardware needs to support that hardware file, right? That model file. So you also need to like think about the tools that you use as well to generate your final model file. Um, and the unfortunate reason for this is that there's just a lot of standards. There's a lot of interpreters, compilers, and like different formats for model files. And the ecosystem for this, in my opinion, is like really fragmented with like a lot of tools that don't support all the devices. Um, and I'm not, and this is not really a fault of like the people who design the tools. It's just like a challenge of the field as a whole, right? Because there's like so many types of hardware that we have. It's kind of hard to build tools that support all of them. But because of this, interoperability of your model files is an issue. So let's say your model is trained and optimized for like one device. Let's say like an Intel neural compute stick. That model file, you can't use it on a non-Intel device at all, right? Um, so that causes like this issue. um, the reason we have it this way is that efficient like systems that are really efficient and that have low latency, you need to have like a really strong coupling between the hardware and the software to make your systems efficient, right? um, but then but then because of this strong coupling, changing one part, like either the hardware or like let's say or the software, if you have to change one of them for whatever reason, um, you will have to like rebuild your whole system. There's no other option because of the fact that there's so little interoperability. um, and so these are like and so like how do we like deal with this? um, Again, the answer in my opinion is just look ahead. Look ahead to what your system will be and the requirements of your system. Because changing either your hardware or your software is hard. So when you are building your system, make sure you have finalized the system requirements and the system like constraints and any requirements from your customers or your clients before you actually start building your system, because changing it later on is going to be a pain, right? But even if you have to, there's like some hope. So for instance, there's ONNX, which is great for converting models from one format to another. um, and also like coming back to like this point of system look ahead, choose tools that fit your hardware, right? Don't choose tools that are partially supported or may not like or just supports a few features. But choose the tool that was built for that hardware, because that is what will give you the most performance advantages. And choose it even if that tool lacks features, right? And I think like a good example of this is like Intel devices which support OpenVINO. So for instance, OpenVINO doesn't support like let's say pruning, right? But if I were to deploy a model on a neural compute stick, I wouldn't choose any other tool. I'd use OpenVINO even if I know I can't prune my models, because that's the tool that will give me the most performance. Same thing with Arduino, use tools that is supported by it, like Edge Impulse and TF Lite. Okay. The next part is benchmarking your system. So when you so benchmarking is like this is this technique obviously to measure the performance of your system to see how well how well the system performs. And and traditionally, what we have been doing is we have been and what many researchers have also been doing is they've been trying to reduce memory and flops of the model while trying to maintain accuracy. So this might sound good on paper, and it will give you like results that are really good that you can publish to really good conferences. But they actually recent work has shown that they actually are they don't tell us the whole picture, because these metrics, like memory and flops, these are what people are calling proxy metrics, and these are metrics that like on paper sound good and it's easy to measure without knowing your final hardware that you're going to deploy to. But they don't actually correlate they don't actually correlate with the actual runtime metrics that we can measure using perceptible metrics like latency and throughput and energy. So even if you have a model that has low memory and low flops, it's not necessary that it will actually perform better than a model with slightly higher like memory and flops, but with a better architecture that is more supported on that device. Like just like the example I gave you of like resonance and inceptions, right? And so when we actually perform neural architecture search or any other kind of optimization, if we only look at memory and flops and don't run our like final system or our final model on the actual target device, we our results will be misleading. Um, and this is kind of the challenge that we have when we try to benchmark TinyML systems. So what do we do to solve it? The easiest thing is just benchmark your systems both on host and on device. So some metrics you can benchmark on host, like let's say the accuracy of your model, but then other metrics like latency, throughput, the latency, throughput, and like the energy consumption of your model. These are things that you have to measure on your actual device. I know this might be painful, but it is what will, like, at the moment, unfortunately, it is the best way to get the real metrics that your system will have, right? But there are ways to kind of get close approximations. So we have services like Renode and Edge Impulse that give us approximations, and I'll show this in some time. Also, I will, and like this is kind of controversial, but I also want to talk about using accuracy as a metric. And accuracy is used, or any of its other other metrics, like let's say MAE or MSE. These are often used when we deploy large systems like MLOps level systems. But in my opinion, it's really not that useful for TinyML systems. Instead, like what I think is more useful is like you actually optimize for what really matters, which is like your true positives or your false positive rates. Let's say you're deploying a model to as a camera trap that checks for the presence of like endangered animals. You could have a model that has really great accuracy, but then it also generates a lot of true positives, which yeah, a lot of like true no, not true positives, my bad, like true negatives, which you don't want your system to have, right? If for instance, like if an endangered animal walks through and it gives like even if the model has really high accuracy, but then like it gives you a negative, then your system is kind of useless, right? So optimize for like what really matters to your system, and in this example, optimize for like your true positive rates, right? Um, and also use confusion matrices to spot these issues. Um, and finally, like my second controversial take is, or accuracy, or like like any of these metrics, this should kind of be the last thing that you optimize for. And you should kind of focus first on optimizing for latency and throughput and all of these things, because it's kind of really easy to get an increase in accuracy over time with better data, better techniques, stuff like that. But having a system with low latency, or a really high latency or high energy consumption will hurt you in the long run more. Right? Okay. So finally, we've done all of these things, and these are all like stuff you do on device. Not on device, my bad, like on host. And now we move on to like on device, right? Where like our target deployment device. Um, so when you're doing MLOps, you usually like deploy to containers, but containers, aren't really there for edge devices yet. But actually, like that's not completely true. There's this company called Hammer of the Gods who are working on it. But like I checked a few weeks ago, and they still don't have like a product out yet. But I'm really excited for this. So if you don't have containers, how do you actually manage your, how do you actually manage to like package your applications and deploy it? And also like, how do you use like, let's say, cloud platforms to deploy your devices, right? Um, so what you usually do is like you like use like some like cloud service providers like Azure or AWS, and these have like these device management tools that you can use to send updates to your device and like deploy models to them. Another thing to keep in mind when deploying models is that you have to like take steps in your deployment to reduce battery power consumption. Um, and there are ways to do this. So make sure your model, make sure your device is on sleep mode a lot if it's not being used. Um, and reduce the amount of data that you log or you transmit. And finally, you can sensors actually like also take up a lot of energy. So use sensors that are low power, sensors like neuromorphic sensors. So you have neuromorphic cameras and stuff. So in my experience, I think like logging and transmitting will take up like 80 to up to like even 95% of your battery power. Um, so yeah, like keep this at a minimum when you are deploying your system. There are also a few deployment architectures that I want to talk to you about. The first one is this concept of multi-tenancy. So when I talk about multi-tenancy in MLOps systems, what this means is like different users can get different versions of the same model. Um, and But this is not something that is kind of that important for edge computing. Instead, like in edge computing, you can have concurrent multi-tenancy architectures where one device runs multiple models. So you could have like, let's say, okay, yeah, I'll give an example of this in some time. But before that, I want to talk about like model placement, where let's say you can have like one model deployed to one core, or maybe like an accelerator or something, and another model deployed to a different core, or like another device. And so if you place your models like in a smart way, you can actually reduce a lot of your battery power consumption. Um, A good example of this is the neural compute stick that I was talking about. It's an accelerator that you can like plug into your Raspberry Pi. So you can have like a really large model deployed on the neural compute stick, and a smaller model deployed on the Raspberry Pi itself. And so, you know, like the smaller model can act as a gateway to the bigger model on the Raspberry Pi. And this is called like a cascade architecture, where one model acts as a gate to a bigger, larger model. And that larger model could even be deployed to a cloud device, right? So your smaller model you can optimize it to have a really low true positive, like a really low positive rate, so that the bigger model is not run often, right? And that'll help you save battery power and help your system run faster. Um, Another thing is about multi-tenancy is like fleet-wise multi-tenancy. So um, you can have like a whole fleet of edge computing devices, right? But then it's not necessary that like let's say a fleet of animal tracking devices in like a forest, the model that is deployed over there will not really work well if you know, if you're deploying another fleet to like in like a desert or something, right? Or like in some mountainous region. Um, so yeah, so you can have fleet-wise multi-tenancy where you have slightly different versions of the same model running in different parts of your whole fleet. Um, so yeah, so these are some of the architectures that I want you to kind of think about when you deploy models. Finally, like after you deploy your model, it's also kind of important that you can monitor your TinyML device. So, you know, this helps you check if your device is actually working. It also helps you check for like damage or like, you know, if your battery is running low, and you can fetch logs and stuff. But the problem is that monitoring requires like a lot of power. Um, and that poses a problem, especially if your device is battery powered, right? Um, so how you can monitor is like you can either have your device send requests to the cloud, which can like using either like a cellular network or like Wi-Fi, which will take up a lot of power, or you can have like a gateway that connects to multiple uh, devices, it's like TinyML devices. So your TinyML device sends some data to the gateway, and the gateway then sends data to the cloud. And this will usually help you save power because you can use like a really low power transmission protocol, and then your gateway can be powered and use something that is like transmit data using something like cellular or Wi-Fi, which which is easy but also consumes a lot of power. Um, the challenge really becomes like comes when you're trying to monitor your device without any network connectivity, and this is like not really that easy to do. The only system that I have seen that can kind of work in this situation is like mesh systems, where one device is connected to another TinyML device and they're all kind of interconnected in a mesh, and then they finally connect to a gateway. And I know that you know, like a lot of devices a lot of manufacturers were working on this. So I know Particle was working on this a few years ago, but then last year they kind of just stopped, and that's really unfortunate because the technology was like really cool. um, what about updating your models? So yeah, it is important to update your model because you may want to deploy retrain models, or you may want to deploy a model with like you may want to update your firmware to something faster, or you may want to like add functionality to your systems, right? So you can update your model by a few methods. The first one is federated learning, which is like really cool, but then there isn't really a lot of work being done in this area for TinyML devices. There's also on-device training that you can do to update your model. But then this takes a lot of power and again, like doesn't work really well and not a lot of work in this area. And finally, what you can do, and like the easiest thing you can do is like use gateways to just receive updates, and then that gateway sends data to a lot of tiny ML devices. Um, but this like technique of like updating, it's kind of risky, because if you have like an update that fails, then it can like turn your device into a brick like for good, right? And so that's why you need to have systems that automatically recover from updates that are failed. And you also need to make sure that when you do update, you send those updates securely. Um, and finally, you need to also make sure you do like partial updates, like if your device supports it, so that your battery consumption is lowered. So for updates, like most of these device management tools, like Azure IoT or AWS Edge, they support it. I know Particle supports over-the-air updates as well. Um, but yeah, make sure that your system has these capabilities to update and monitor your system. Uh, okay. And finally, I want to talk about security of your system. Um, and so there's been a lot of work recently that shows that you can actually use side channel attacks to actually steal model files present on devices. So you can use like let's say, and these attacks are actually really simple to do. One of these attacks is where you use like one of those cans that have like air in them to freeze the RAM of a device, and then you can dump the contents of the RAM and extract your models. So yeah, so it helps if your device is going to be deployed to an area where it is possible that there might be attackers trying to get the model, or like, or if you're uh, um, uh, or if your model has like some IP, then yeah, make sure your device is protected from such attacks. I also want to talk briefly about robustness. So robustness can mean robustness to like sensor failure. So what if like your camera, like a few pixels of your camera stop working, or like let's say like there's some dust that falls on your camera, or like your pressure sensor or something that makes it give weird readings. So you have to make sure your model is kind of robust to that. Network failure is also something that you need to make sure your system is robust to, like during updates or like when you're monitoring your device. And another thing is like graceful degradation, where let's say your device's battery is running low, then how do you like smartly turn off some parts of your device, so that even if the battery is running low, you can make sure it lasts a bit longer by turning off these non-essential parts of it, right? And finally, redundancy, because your devices may be deployed to like in like rough conditions, or if your device may be performing some really important tasks. You need to make sure there's redundancy built into your device and your hardware. And a good example of this is like the Tesla a chip that Tesla made, their fully self-driving chip, which actually has two of everything. So even if one fails or something happens, there's another one that will take over and run and make sure your device continues to run properly. Okay, so thank you so much. And I want to like move on and show a demo of some of these things uh, in Edge Impulse. So I didn't. So I know that you've probably been seeing a lot of this stuff throughout the last few days. So I don't want to go too much into detail about the tools that Edge Impulse has, but I do want to cover some of their tiny ML ops related tools. And one thing that I want to talk about is if you go to your dashboard and then scroll down to the right hand side, you can actually choose a device that you plan to deploy your model to, and Edge Impulse will kind of figure out what the latency and the the memory and memory consumption will be. So you can just choose your final device and let Edge Impulse kind of handle that, right? Um, Another thing is you can use you can use these blocks to create your own system, but what would be even better is if you have a system that actually tunes your builds the whole pipeline for you based on your system requirements. So here you can actually show, you can select the target constraints of your device. So for instance, I can choose let's say 100 milliseconds as my final target for deploying my model, right? And then the Eon tuner will kind of make train multiple models that meet that requirement. And this is like a form of the look ahead method that I was talking about before. Um, so so here, let's say, and another good thing is they actually show these graphs of performances, which is really helpful as well. So let's say this particular model, not model, pipeline got 100% accuracy. But then if you look at the timing, you can see that like more than half of the time that it takes to make a prediction is spent in doing data pre-processing and DSP stuff, right? Whereas on this side, you're spending less time doing DSP and more time doing model prediction. And you can use this information to kind of choose which will be suited best for you based on what future requirements you may have. You may want to, let's say, I don't know, deploy something else on the same device that uses the onboard DSP. In which case you would want your ML stuff to use the DSP for less time. So you can choose a pipeline that does that, right? Another thing I wanted to show you was when you go to actually deploy your model, you can choose how you want to deploy it. So you can choose the hardware, and you can choose how you want the library you want to use to deploy. And this is also really helpful because, like I said, different hardwares can support different libraries and firmwares and tools, and you can choose that and build your final deployment firmware, right? And finally, let's say you deploy your model and then you want a way to update it. So Edge Impulse has their own API that you can actually use to so you can actually call these APIs from your gateway or from your edge device itself, and then fetch the trained model. So the model won't be trained on the device itself, but you can have the model send the data to Edge Impulse's API. Edge Impulse will kind of do all the training, tuning, and build a firmware package that you can then use to update your device. And I think this is really powerful, because of how easy it makes doing over the air updates and to retrain models. Okay, so I think I've been talking for a long time. Archana, are there any questions?
Um, Yeah, so there was one in the start which asked, are there tools or best practices mechanisms for on-device A/B testing of competing models to compare differences in inference using identical data at scale?
So if you're talking about doing A/B testing on the target device as itself, that's going to be difficult because your target device may not even have enough memory to save two models on it to do A/B testing. What you could do instead is have like some devices that's running one model and then another device that's running like another like the different model, and then do A/B testing like that. So do A/B testing like fleet wise, where like some part of your fleet is running one model and another part running a different model, and then you can check the logs and choose a good model based on that. And that's the kind of deployment architecture that I was talking about before, where you have like fleet-wise multi-tenancy where different models are deployed to different fleets, and that like that's how you can do A/B testing.
Yeah, I guess that was the major question we had. Apart from that, I think others were answered already. So yeah, let us. I think we have less than 3 minutes left. So
So yeah, so we also wanted to kind of talk a bit about like a package that we are working on for tiny MLOps. So we're working on this package called Scale Down, that we're actually like, we've seen that there's like a lot of these systems that like you need in an MLOps, like a tiny MLOps pipeline. And we just thought, okay, like let's try and make something that can help people optimize their model, benchmark it, and then deploy it. So yeah, we're working on that, and we'd love to like get your feedback and suggestions for that. Um, we're also actually working on like what we've talked about today. It's actually something that it's like there's not a lot of material for it out there, and so what we're doing is we're actually working on a book. Like, it's open source, it's online, you can go check it out right now. That where we're putting all of these ideas in the hopes that like the community like kind of benefits from it. Yeah, so finally, like, I hope like we got you excited for this. And we'd love some of your feedback and to help you like to help us improve how we presented what we presented. And if you have any questions and stuff, you can use this QR code, and like give us like some feedback. It's completely anonymous, and then you can get a link to the slides, and all of this. Also, like, I think this video will be up on YouTube, so you can take a look at that later on as well. So finally, in conclusion, I really want to stress again on this look ahead method. It's really, really powerful, and you can use it for training, and for optimizing, and also when selecting your software and your hardware stack. I also want you to think about how you deploy your models. So you can have like a cascade architecture, or like different forms of multi-tenancy architectures, and to make your deployments more efficient. Another really important thing I want you to like think about is, when you are creating a system for TinyML, make sure you always leave some space or some performance, so that in case you have to add extra features later on, you can do that. And finally, monitoring your models, updating it, and then security robustness. These are things that might seem difficult to do, and you might think, okay, fine, let's leave it, let's not do it. But don't do that. These are actually like really important things, and you should think about them when you are building your TinyML system. Okay, So that's it. Thank you so much, Edge Impulse, for giving us this platform. And yeah, if there's any final questions.
Yeah, there
Uh,
is one. So yeah, let's just quickly answer it. Will it be difficult to integrate tiny MLOps into pipeline setup on AWS or GCP?
That's a good question. So it depends on what your AWS and GCP pipeline is like. You can actually do, so let's say you're training your models on AWS and GCP, and then you're using, AWS's edge tools to, send updates to your, like to manage your edge computing devices. So in between, you'll have to benchmark your model, and then you'll have to optimize it and then benchmark it. These are things that you can do in AWS and GCP. So you can actually optimize like your model over there, but then you can't really benchmark how well your model is doing on like you can't benchmark your latency and throughput. So that's something that you will have to, like it. You can make that system kind of automated. You'll have to download your model, load it to your target hardware and measure your latency or throughput to get like the real metrics. Or you can use Edge Impulse or Degree Node to get like a good enough approximation. Yeah.
Okay, I think we are done. But yeah, thank you so much everyone for joining in and listening to us today. And thank you so much for your time.
Thank you.